Right. Here's what we learned before. Okay. On the surface, explaining space, we have so-called Garden map, which can be defined using Gaussian map. Okay, so that's a couple of things we need to know. Right, this is the surface. Right, and at every point there is tangent plane, which is a two-dimensional vector, two-dimensional vector plane, and so we have a so-called Wingard map, which is a linear map from tangent plane to tangent plane. And on the tangent plane, we do have an inner product, right? Now there was a couple ways to define inner product. One is this is the usual way, it's dot product, right? And this also written in that form. Okay, this just we view tangent plane as a vector, as a subplane in three-dimensional space. Okay, so use a inner product from Euclidean space. You can define the inner product two vectors. This is a U. That's a U. That's a W. Okay. Okay, and the very important property is about this is going to be self at the joint. Okay. Now in linear algebra, we can find this is a linear algebra. Okay, it's a linear algebra. There's also normal basis. Normal basis E1, E2. Also normal means the dot product with itself is going to be 1, and this is going to be 0. Okay, such that W1 is going to be K1 E1, and W2 is K2 E2. Okay. So that is a very important property for linear algebra. Okay, so we're not going to spend time to go over the linear algebra. What we know is K1, K2 is definition. Based on this fact, K1, K2 are called the principal curvature at the point P. Okay. Now, but for an arbitrary basis, this is another linear. Okay. For an arbitrary basis, B1, B2. Okay, for this plane, you can have a matrix, right? So AB1 plus B2, okay, and WP B2 is CB1 and D B2. So you get a matrix. Actually, you get a matrix. You can also write like this. This is I use this kind of letters because that's not a real vector. Each element is a vector. It's B1, B2, and here I got A, B, C, D. So this match is not necessarily be symmetric, okay? And maybe, right? How does it? Yeah. This is just an arbitrary basis. Okay. Okay, so this is a matrix, and we know that the eigenvalues of a linear map is independent choice of a matrix, a basis. So K1, K2 are the roots of the so-called characteristic polynomial of the linear map, okay, of the roots of this map, okay, A, B, C, D minus K, K, 0, 0, okay, this is going to be, this is called the so-called the characteristic polynomial of the matrix. And this matrix is really independent of the choice of a particular basis, okay? That's another linear. Okay, so this is going to be K1 minus K, K2 minus K, actually. Okay. And this is because when you choose another basis, what you get is the new matrix will be similar to the original matrix. That's why the characteristic polynomial will be the same. Okay. So that's linear algebra. So we're not going to spend too much time on linear algebra here. So this is another way you can calculate K1, K2. Now it's much harder to find the orthonormal basis such that this is true, okay? And in other words, here, W, E1, E2 is going to be E1, E2, and here's K00, K1, K2. So it's not easy to find the orthonormal basis such that this holds, okay? So what we do is we take an arbitrary basis and you get a matrix, and then you find the determinant of this difference of the two matrices. Then the roots of this quadratic function is going to be the roots of this quadratic equation are going to the principal curvatures. Okay. Now, if we have to find the principal vectors, then you have to find the orthonormal basis. Okay, so B1, B2, E1, E2 here, EI is called the principal vector corresponding to Ki. Okay, so if you have to find principal vectors, then you needed to find you have to find find eigenvectors. Right. So how does so remember the normal curvature, right? The normal curvature, okay, the normal curvature, okay, is going to be defined by the second fundamental form. Okay. So this is just a review. Normal curvature in the direction V, okay, is going to be, this is the length we assume is going to be 1. Okay. Then this is going to be actually this is Wingard map, right? And the dot product with itself. Okay. So we can express it in the form such like such like cosine theta E1 plus sine theta E2, right? Because this is a E1, that's E2. So any vector, right? This is a theta. Any unit vector, right, can be expressed in this form. Then this is a normal curvature N, right? it's going to be W, right? Cosine theta E1 plus sine theta E2, and here's a cosine theta E1 plus sine theta E2, right? So when you this is a linear map, so it's going to be cosine theta K1 E1 sine theta K2 E2, then dot product with cosine theta E1 sine theta E2. So E1 dot E2 is going to be 0, so that's why you only get K1. You can get K1 cosine square theta, K2 sine square theta. Okay. Okay. Now, we may assume K1 is less than or equal to K2. Okay, that's it's not a big deal, right? Assume, sorry. Then we look at this normal curvature. This normal curvature, K1 cosine square theta, K2 sine square theta, right? It's going to be less than or equal to K2. Okay, because K1 less than or equal to K2, so K2 then cosine square theta by sine square theta equals 1, and greater than K1. Okay, so normal curvature is between two principal curvatures. Okay, so this is about this thing. Okay. Okay. So without using any surface patch, that's what we can talk about. Okay. That's K1, K2. Now, in realities, we just given a surface patch. We are not the natural basis for the tangent plane, and not also going also normal basis. Okay. Where's my file? My file is gone. Hold up. Okay. So how to compute it? When you're trying to compute it, this is so we have a basis, right? So this is a point. Here's a surface edge. This is a domain in the UV plane. Okay. Okay. Now you get the basis. One is sigma u, other one sigma v. Okay. And in general, sigma u, sigma v is not an orthonormal basis. Okay. Okay. For the tangent plane. Not only that, the Ringarden map, they're not the principal directions even. All right. So so how to find principal curvatures? Okay. Well, remember we at the very beginning already mentioned that the right, if you can find, yeah, you can find the basis for arbitrary basis, right? If you can determine this matrix C sigma u plus D sigma v, then okay. then the curvature, principal curvatures, K1, K2 are the roots of this determinant, right? A, B, C, D minus K0, 0, K, okay, right? So all I have to do is find the ABC, right? Once you find the eigenvalues, then you can get eigenvectors. And then using the eigenvectors, actually you can show that they are orthogonal to each other as long as K1, K2 are not equal to 0. Okay. So that is yeah, so let's go back to what I said at the very beginning. Okay. You see, linear algebra says there is an orthonormal basis E1, E2, right? Satisfying this. So what we did actually is we not find the E1, E2 first. We find that in order to prove this, step one, okay? Step one, you have to show, you find the matrix, right? Take an arbitrary basis, you find the matrix, then you get eigenvalues first. And using eigenvalue, you get corresponding eigenvectors. If the eigenvalue are different, then those two eigenvectors must be perpendicular to each other. Then you normalize it, and you get an orthonormal basis using eigenvectors. Okay, and if K1 equals K2, in that case, the eigenvalue has multiples of 2. So after you find the first one, you try to find another one because then that's a little bit tricky, yeah. Then you still get two orthonormal, there are two perpendicular eigenvectors, okay? Two perpendicular eigenvectors, so then using those two eigenvectors, you can get this E1, E2. Normalize it, but they're all perpendicular to each other automatically. So that's the idea, okay? And here we actually, in the first step, trying to find the eigenvectors, eigenvalues, and find the eigenvalues using its matrix. Okay. So given arbitrary basis, you get a matrix. Okay. Now, what is A, B, and C, D? Okay, what are A, B, and C, D? Recall that this is going to be negative nu. Okay, the partial derivative of the normal vector. This is negative nv. Okay, so actually you are going to using this to find the A, B, C, D. Okay. Right. And after you multiply, we did it in the last class. So let me show you what we get here. My notes. Okay. After you multiplied, dot product was dot product was sigma u and sigma v respectively yield the following: L, M, M, N, and here E, F, F, G, and A, B, C, D. Okay. So A, B, C, D, in other words, is going to be E, F, F, G, the inverse matrix, and L, M, M, N. Okay. So now let's take a look at the determinant. Okay. A, B, C, D minus the identity matrix, right? 1, 1, 0. Okay. So I'm going to replace it by, this is a linear algebra, FG LM MN minus K 1001. Okay. All right. So I take this matrix out. So this is going to be EF FG, the inverse, right? And here LM MN. And this matrix, okay, this is identity matrix, so that's why you have to have this part. If you multiply this out, you will get this part and that part, because the inverse with itself is going to be identity matrix. Now, we're using the important property in the determinant. Determinant A and B is determinant A times determinant B. That's already proved. This is a fact, okay? For any square matrices A and B. So that's why it's going to determinant E, F, F, G, and then the determinant L, M, M, N, minus K, E, F, F, G. Okay. So the first part is never be 0, and this is going to be 0 if only if the second part is 0. Okay. So K1, K2 are the roots of the following matrix. At L, the difference is minus KE, M minus KF, M minus KF, and N minus KG. Okay, this can be 0. Okay, so that's it. So you can use this formula as after you compute the EFG, LM. First fundamental form, second fundamental form, then just use the coefficients. Okay. Now, if you want to find the eigenvectors, how do you find the eigenvectors? How to find the eigenvector using EFG? And how to find the eigenvector? Okay, call it eigenvector. Okay. Come on. Corresponding to the eigenvalues. To K. K1, K2, right? Ki. I start from 1, 2. Well, remember this is going to be the eigenvectors, right? A, B, C, D. And the eigenvector, I'm going to call it's a notation in this book. I don't want to create a new notation. This is possible. A times CNN. Okay, so that is going to be supposed to be Ki. Okay. Then look at this identity, right? So this is actually is going to be A, B, C, D minus Ki, 1, 0, 0, 1. This is a matrix. Because this matrix, the determinant is 0, so that's why you should have a non-zero eigenvector. 0 vector satisfying this equation. Okay. But remember, this is just the the inverse matrix, right? So it's easy to check E, F, F, G. Remember, right? We have L, M, M, N, K, I, E, F, F, G, right? Since this is the inverse matrix, doesn't matter, you can remove it. So this is equivalent to saying E, E and FG. So you get you have to just solve the system of a linear equations. Yeah. So this is a E, F, F, G. Okay. So this is how do you can, yeah, you use a determinant, it's a 0, right? Then you also have a use as the eigenvalues, and then this matches because for eigenvalues that the determinant is going to be 0, right? And because this the eigenvalues as the roots of this determinant. And so you can always find the non-zero vectors. Right? That's how do we find the principal curvatures. Okay, now in case K1 are not equal to K2, you can show that those two eigenvectors are perpendicular to each other. Okay. And then you can use this property, you can find an orthonormal basis. And each of them are the eigenvectors, or we call the principal vectors corresponding to the principal curvature. Okay, let me check. How do you? Yeah, here's the fact. Okay, in linear algebra. Oops. I'm trying to. I don't know. I need to charge my pen. I don't know when to run out the battery. All right, so if you have two eigenvectors corresponding to two principal curvatures, if those principal curvatures are not the same, you can show that those two vectors, the principal vectors, are perpendicular. Okay, that's great. So then you find also a basis using it. Let me wait for a minute. Right. So this is a fact. If E1 equals K E1 and W2 E2 equals K2 E2, and K1 is not equal to K2, then E1 E2 must be 0. Okay. The proof is simple. Okay, what we do is W E1 E2, right? And it's going to be E1 WP E2 by itself adjoint. But this side is K1 E1. This side is actually K2 E2. So they're equal. So you move the right term to the left-hand side. So K1 times K2, K1 minus K2 times the inner product should be 0. Now, since this is not going to be 0, that's why the inner product must be 0. Okay, that's it. If if both K1 K2 are equal, okay, then from linear algebra you can even show that there's a two linear in the solution space. Okay, it's two-dimensional, so you can find the two eigenvectors corresponding to the same K. They're linearly, independent. Then you can find a pair of orthonormal eigenvectors. Okay. So this is how do we, if we're given surface patch, then they're not, This is how do we find this principal curvature, okay, and the corresponding principal vectors. Yeah, by solving the above equations. Okay, let's take a look at the following example. This is a let's see. This is a cylinder. You know, okay. We can also study a little bit more general surface of revolution. Okay, let's take a look at cylinder. The cylinder. I can, before I solve the problem, I can imagine, okay, for the cylinder, okay, this is x squared plus y squared equals 1. I can tell that K1 may be 1, K2 should be 0, and the E1 depends on where the point, it should be in that direction, that's the E1. And the E2, okay, E1 is E1 at every point, you know, you can look. So E2 is a vertical vector, okay? And it depends on where the point you choose. Okay? So if we parameterize, it's being cosine V, sine V, and the U. Okay. Then sigma U is going to be 0, 0, 1. Sigma V is going to be negative sine V, cosine V, and 0. So I think it's better to switch the order, okay? Let's say K1 is 0, it's 1. Okay, so E1 is going to be sigma U, and E2 is a sigma V. Okay. So these two natural bases from the surface page. This natural basis from surface page is actually also normal basis. Okay. And let's prove it. To do that, we just needed to take a look at also normal. There's a normal vector. Okay, we can find this directly. Okay, not necessary to go through the E, F, G, M, L, N. Okay, that's actually more complicated. So the normal vector is sigma U times sigma V. Okay. So sigma U is going up. That's E1 and C2. So let's see. This is point to inside. I'm pretty sure. Yeah, it's point to inside. So IJK 0, 0, 1. Okay. So you will get negative cosine V, negative sine V, and 0. Okay. So it's point to the inside. This is the N. Okay. Now, so NU is going to be 0, 0, 0, right? NV is going to be sine V and the negative cosine V and the 0. Which is going to be negative V. All right, so now we got map. Okay, NU, it's going to be 0. Okay, 0 vector. So it's going to be 0 times sigma U, right? You can say that. And right. And for this one, it's negative nu, so sigma v, which is going to be 0 times sigma u plus 1 times sigma. Okay. So our matrix right? And you will see that K1 from here, K1 equals 0, and K2 equals it's 1. Okay, and the corresponding principal curvature will be sigma. Okay. Those are the principal vectors. Right? So there is no need to find the ML, and EFG, and you can see that from here directly from this green garden map. Of course, the product of these two matrix, two curvatures is going to be 0 because then the Gauss curvature is 0. Let's take a look at some examples. Okay, here's another interesting example. We have the so-called, this is from previous example. Okay, so this is a surface patch for the surface, and theta rho. Okay, it's going to be a plus b cosine theta cosine phi, a plus b sine theta, cosine theta, and here's a sine phi and b sine theta. And this is actually the torus. Okay, and it's a yeah. Let me draw the picture for you. That's page 2. Yeah, please. Yeah, this is fine. So here's a picture. Yeah, it's a torus. Okay. Now we want to find the principal curvature. We hope we can even find the Gauss curvature and the mean curvature. Okay. And somewhere the curvature may be negative, somewhere curvature is positive. Now how do we do that? Okay. Well, we just define the derivative. Okay, say that. Okay. So the derivative of cosine theta is going to be negative b sine theta cosine phi and the negative b sine theta sine phi, and then that is going to be b cosine theta, right? And sigma phi is negative a plus b cosine theta sine phi, and here a plus b cosine theta and cosine phi and 0. Okay. From here you can see what is the e, right? E is that square plus this square. Then okay, we should know which one is first, right? Yeah, that's the b square. Okay, and this and f I think it's going to be 0 because cosine phi sine phi is going to be positive and negative, so it's going to be 0. And g is going to be it's going to be also this is going to be a plus b cosine theta and the square. Okay. That because sine phi square plus cosine phi square is going to be 1. So this is the EFG. Okay. Now we needed to find the we have to find out how do we find the LMN. Okay. To find the LMN, there are a couple ways to do. We can use a normal vector, right? And then the second order derivative. Okay. Yeah, what is the best way to find the second fundamental form? Well, the traditional way to find the second fundamental form, you use that definition, right? LM is going to be but anyway, you have to find a normal vector, right? Yeah, otherwise, there's no way you can find this normal second fundamental form. Okay, so from the definition of the second fundamental form, okay, you still have to use a normal vector. Anyway, so let's find the normal vector. Okay, sigma. Okay. Let's finish this part. So I, J, K, I'm going to put, yeah, this is sigma, it's negative, right? Maybe I just put I, J, K here on the top. So the first one is going to be negative b cosine theta, a plus b cosine theta cosine phi. Okay. Because just look at this matrix, right? Yeah. Then you look at the matrix in the middle. Okay. So it's minus, so it's actually negative b cosine theta, a plus b cosine theta sine phi. Okay. Finally, the last one is going to be the same constant. Okay. And here's a b sine square, b sine theta. Okay. and you have a cosine square phi, and it's minus cosine square phi plus sine square phi is going to be 1. Okay, so the normal vector will be, this have to be taken out. Okay, this should be removed. Okay, and also the b is going to be removed. Okay, so normal vector is going to be negative cosine theta cosine phi, negative cosine theta sine phi, and then sine theta. Okay, this is a unit vector. Now, when you square it, okay, when you square it, you get cosine square theta, then plus sine square. So it's what? So this is a normal vector. Great. So once you have this normal vector, then all I just needed to do is just find a second fundamental, order derivative. Okay. So sigma theta theta. Well, I just have to go back. The screen is too small. So it's a negative. Yeah, becomes cosine theta, right? So negative cosine theta cosine phi, negative cosine theta sine phi, and then there will be negative phi sine theta. Okay, because here's a cosine theta here, right? Okay, and I needed this one. Okay, this one will be negative b. I think this is a, you see, I keep forgetting. Yeah, this sine theta and the cosine phi becomes sine phi. Okay, because I have a, yeah, negative becomes negative positive. Okay, it's going to be, so this is a positive. Okay, b sine theta and then cosine phi. Yeah, there was a positive sign here. Yeah, let me check. I have a negative sign. Yeah, and this will be negative and the 0. Okay, sigma phi phi. Yeah, let me compute. Okay, so this will be negative. Okay, so it's negative a plus b sine theta, and sine becomes cosine, and then cosine becomes sine. Okay. Yeah, wait a minute. Yeah, that's cosine theta. Okay. Let me erase this. I keep forgetting this, but the space is a limit. Okay. So that's it. Then yeah, cosine phi becomes sine phi, right? Sine phi becomes cosine phi. Okay. So both are negative. So now, okay, L is going to be the dot product. Okay. It's going to be sigma theta, and n. I'm going to do a product here. Okay, it's going to be negative. I think it just be square. Just a b. Okay. And the m, I think it's going to be 0. Sigma theta phi dot n, it's going to be 0. The reason is So I have opposite sign and that canceled out. And a little bit tricky here, it's going to be a plus b cosine theta. I think I have another cosine theta from here. Yeah, cosine theta. Okay. Yes. Okay. So those are the LM. Okay. Now we find the E and F, G and LM, and how do you find the eigen? Right? To find the eigenvalues, you have to find the determinant of, remember, M minus K E, right? And M minus KF and M minus KF and G minus K, no, so MN minus KG. So that's give me 0. Okay, so let's put the details here. L is going to be B, right? And E is going to be K and the B squared. Great. Okay. And the M minus K, M is 0, K is 0. Okay. So N is going to be A plus B cosine theta and cosine theta. K, and here A plus B cosine theta squared. All right, so that's going to be 0. This can be 0. This is a product, right? So it's easy to see. That's the first term. And the second term, I think I can take the constant out. All right. So what I get is that K1 is going to be 1 over B, right? And K2 is going to be cosine theta, A plus B cosine theta. All right, theta is, yeah, let's go back to this picture again. Okay. All right, this is, I think, what is my angle theta? Okay, angle theta is this one. And the phi disappear. No, that's the phi. Yeah, the theta is this one. This is a circle. Inside the circle, there is a theta here. Okay. You see, for any phi, the surface of this section is identical with others, similar. Okay. So that's why it's yeah, let me explain to you why this is independent of phi. Right? Because look at this, right? It's a cylinder, right? When phi changes, you look at this circle on this torus. Those circles where actually is no bigger, no, they all are similar, right? So geometry of this part is the same as the geometry of that part when you rotate. Okay, so the curvature should be independent of a particular value of phi. Okay. Okay, but when you on the same circle, right? If the angle theta changes, then the surface it's more curved inside here and less curved outside. I think so. Okay. Okay. I'm pretty sure this is if this is a vector E1, E2, I think E2 should be in that direction. E1 should be in this direction. Okay. because it's constant, right? Or this circle, the curvature of the circle is constant, but inside the surface is more curved than the surface outside. Okay, so let's see the Gauss curvature. The Gauss curvature is going to be K1 times K2. And that is going to be cosine theta B A plus B cosine theta. Okay. And when the Gauss curvature is negative, well, it depends on cosine theta, right? So Gauss curvature is negative if only if theta is greater than a pi over 2, less than 3 pi over 2. Okay, so that is the circle. Okay. So this is the angle theta. Right, this is one of the cross section. So here the curvature is negatively curved, and here the curvature is positively curved. So inside the torus, right? This is cross section of the cross. Okay. The cross section, you know, if you draw the picture, it looks like that. Okay. So the outside is more curved, the inside is less curved. It could be negatively curved. Okay. And the mean curvature, we don't know whether it can be negative or not. Okay. The mean curvature is half of the 1 over b plus cosine theta a plus b cosine theta. Okay. Based the construction requires a plus b cosine theta is always positive. Okay, b cannot be too large. So a plus b cosine theta, when you multiply and when add them together, b cosine theta plus b cosine theta. Okay. When b sufficient small, the mean curvature is going to be always positive. Okay, but if b is a little bit larger, but still smaller than a, okay, then the mean curvature could be negative. Yeah, the geometric meaning of the mean curvature we will discuss later. It's actually like a surface with a mean curvature equals 0 means this is called minimal surface. Okay. And the minimal surfaces are very special, interesting surfaces. Locally has a minimal, the area is minimal. Now let's take a look at some theory, okay? We want to study, consider surface, okay? And we want to make sure surface S in R3 was a foreign property, and the principal curvature will be the same. Okay. So here we have a so-called umbilic surface. Okay. So we assume that we assume that when got map is going to be constant. It's always for any v. Okay, and then that means the point. Yeah, the point P is called umbilic. Okay. Now, so we assume this condition. Okay. 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 So, but the P, K is a function of a P. Okay. K here, K depends on P, but independent direction. This is our point. Okay. For any vector, any P on the surface. And we want to understand this. This is in other words, every point is umbilic. Okay. Okay, we studied this concept. So what we're going to do is, I don't know how does it look like, right? This is a arbitrary parameterization. It's called a surface patch. Okay, because we have this property, so sigma u is going to be k. This will be a function of u and v. Okay, where k is going to be a function of uv, because it's a value. This is a function on the surface now, together with at the point, right? At the point, because every point is expressed by expressed using the surface patch, so this becomes function uv. Right. So now, but remember, for the normal vector, right? And this is a negative, right? So that's why I have a negative sigma u and v negative sigma v. Okay, we have these two identities. Okay. So first of all, we know that uv equals nvu, the partial derivative. Okay, using this fact, what we can do, we can differentiate. Okay, and this is going to be negative kv sigma u plus minus k sigma uv. On the other hand, this is going to be, okay, so that can be negative k sigma v, partial derivative with respect to u. So it's negative ku sigma v and minus k sigma vu. So those two sides are equal, and you will see that these two are equal, right? So that means kv sigma u should be equal to ku sigma v. But sigma u, sigma v are linearly independent, so kv should be equal to ku should be 0, since sigma u, sigma v linearly independent. Right? So that means the partial derivative of k is a constant. That means k is going to be constant. So for an umbilic surface, the principal curvature, if at the beginning it's their function of uv, but you can prove that k must be constant. Okay. So constant, there are two cases here. Case 1, k is going to be 0, right? And case 2, k is not going to be 0, right? And because k is 0, right? And u equals what? Remember, we go back to the equation, right? K0. So NU is 0 because it's going to be negative K sigma U, it's 0. And V equals negative K sigma V equals 0. Right, so that means N as a function of U, V is going to be a constant, a vector. Okay, it is in a constant vector. Because it's constant vector, so N dot sigma U, okay, no, not, let's see, this product, I'm going to differentiate with respect to U. Because it's constant, I don't need to worry about that, right? This is always perpendicular, right? And N sigma V is going to be N dot sigma V. Why? NU is going to be 0, that's why, okay, it's 0, okay? So that means N sigma is a constant function. Okay? Its constant function, let's call it C. Okay? So in particular, N sigma, right? You can say N dot sigma, right? It's always like that. And this is a fixed point. So that implies N dot sigma UV minus sigma. Okay. So look at it. This is N, right? This is supposed to be surface. Here's the, right? And here's another arbitrary point. And this is a perpendicular always. N is a fixed, it's constant. So that means this lines in the plane passing through the point P, which is fixed, okay, and perpendicular to N. Okay, in other words, this is a plane, the tangent plane, okay, i.e. the tangent plane. Okay. So that means the surface is a plane, is a portion of the plane. So the surface is a portion of the plane. Okay. Wait. Okay. So the next problem, next case is case 2, when K is not going to be 0. When K is not going to be 0, and remember, N, right? Okay. Right, we have this 2. So I can move the right-hand side to the left. I move, okay, all right? And that means N minus K sigma, it's constant. So this is a constant vector, okay? All right, it's constant vector. So what am I going to do? I'm going to divide both sides by K. Okay, sigma N. It's going to be KA, right? Okay, so length is going to be 1 over Kn. And since this n is normal vector, so it's going to be 1 over K. Now, what does that mean? In other words, sigma uv. Okay. So that means sigma uv, okay, lines on the sphere, This sphere was a center at 1 over K, this, right? And radius r equals 1 over K. And let's put up a absolute value here, okay? Okay, so this is K over A, okay? And this is r equals 1 over K. So the surface is, the surface is a portion of a sphere. Okay, so empirical surfaces are either is an open set in the plane, or it is an open set of a sphere. Okay, that's it. So but all the other surfaces you don't expect the principal curvatures are equal. Okay, they in general are not equal. They're different. Okay, maybe at one particular point they're equal. Okay, and we call the empirical point that particular point. But that's usually an isolated point, or maybe along the some curve. There are some empirical points cannot be that do not unless that do not form an open set on the surface. Because if they form an open set on the surface, that open set must be either a plane or a portion of a sphere. Okay. So for general surface, empirical points are usually pretty isolated, or maybe along one line, one curve on the surface. Okay. So for general, this we already proved that. For general surface, okay, for a general surface, empirical points are pretty isolated. Okay. So like surface like that, maybe only one point. Okay. And that particular point, maybe they're equal. Okay. They're not so many umbilical points there. Okay. And umbilical points are pretty will be interesting points on the surface. We should pay attention. Sometimes we have to find out. Okay, those are the special points. The geometry around that point are quite interesting. Yeah. Okay, so let's stop here.